In statistics, quite often we encounter huge amounts of data, and the problem is it's overwhelming. Here's a set of data. Here's a set of data, kind of what we looked at in section 2.4, the average temperature by decade for all 82 counties in Michigan going back to the 1890s. Wow. So it's a lot of data, over 1,000 pieces of data, and that's just in one column. And then you've got multiple columns. So what do you do with this? What you do with it is that you summarize it. You have to find ways to show that something is typical or decide that it's not typical. Well, first we're going to figure out what's typical, what's representative of our data set. And there's a couple common ways you can do that. One of them, of course, the way that most people are familiar with is the average, or it's called the arithmetic mean. So let's put that down here first. So this is the average or arithmetic mean. And the way you calculate the average, I don't think there's any big surprise here. You add up all your data and then divide by the number of pieces of data in there. So if you had 4 tests and you want to calculate your average, add up all 4 scores, divide by 4. So n is the count of your data, how many pieces of data you have here. And this is the sum of the data. So the data is represented by x, and then this Greek letter sigma represents sum, S-U-M. So the average is fine. It's a nice measure of how what's typical of a data set. But the average has some problems, and let me explain and show you some of the problems here. I'll give you 2 examples that show some problems. Over the summer, I got something in the mail offering a free dinner at the Capitol Grill. That's pretty posh. I'm like, okay, you got my attention with that. Free dinner at the Capitol Grill, you come talk to us, and maybe we'll help you invest your money for retirement, maybe not, etc. And they had this big presentation that they showed to a bunch of people, myself included. And it started out with this. You've got this portfolio. They're investing your money in a mutual fund, and look what happens. You know, for the first few years, it's down, but then it comes roaring back. It's up, it's up, it's up. And on average, after 15 years, it's up 5.67% per year on average. Another fund has a similar track record in as much as its average after 15 years is 5.66%. So the question was, well, which one would you choose? And, you know, in absence of anything else, maybe you would say, oh, well, this one, at least it's a little bit higher. But when you look at what happens to your money over time, if you started out with $1 million and every year you're withdrawing $50,000 because you're retired, etc., with this first fund, at the end of it, you'd have $360,000 left. With the second fund, you'd have over $1 million left. Wow, that's a breathtaking difference. It's $800,000 more in this account than this one. So obviously there must be something more going on to the story than just that. There's more to it than just the average. And what is it? Well, we'll get to that in a little bit. For now, let's look at this one. This is a fictional example of somebody who runs a lot of marathons and their finishing place in these races. So marathon, 26.2 miles, pretty grueling. And overall, our runner does pretty good, except one race, right? So what happens when you run or compete for a long, long time? Your body uses glycogen as a fuel. And at some point, your body just runs out of that fuel, runs out of glycogen, and you literally hit the wall. That's what they call it. It happens around the 20-mile mark of a marathon. All of a sudden, you just die. It's like you literally hit a wall. So maybe the runner hit the wall there, finished 56th place overall. But, you know, overall, that's kind of the oddball, right? Now, that doesn't prevent us from calculating the mean. So how are you going to calculate the mean? The mean is the sum of your data, and if you added it up, that would be it right here. That would be the sum of the x's. That's your sum. How many pieces of data are there here? 11. So n is 11. So divide by n, and that gives us something called x bar. That's your mean. This is what we call the sample mean. So if I divide 77 by 11, I get a mean of 7. Does 7 seem to be representative of how this person typically finishes? No. There's no 7th place finish there at all. And then you got this one oddball one. But what do you think's happening? How come I got this 7 here? What went wrong with our average? Yeah. Yeah. This giant outlier. Well said. 56 is a huge outlier, and the problem with the mean is that it can be sensitive to these outlying values. So it'd be nice to have other ways to characterize our data, other different things to say about them. And that's what we're going to work on next. But let's practice a little bit with the mean here. Hopefully everyone has that entered into a data set. Let's see, let's get rid of this one. So we have that entered here. And let's practice calculating a few things here in Google Sheets. So the first one that I'll calculate is the sum of the data. If you want Google or Excel to do anything for you, you start by typing in equals. In this case, we want the sum. So equals and then sum. If you hit the enter key, it'll finish it off for you. Highlight this, highlight that column. Press enter, and hey, it added everything up for you. How cool. That's our sum. Now, in this case, it's pretty easy. You can calculate just by counting how many pieces of data there are, but sometimes you just really don't feel like counting. So if you want to figure out what n is, you hit equals and then count. And again, you're going to highlight just your data. Don't include the 77 right up above. So that's n, that's your count. Now there's a couple ways you can calculate the mean. If you have both of those values, if you have the sum and the count, that is sum of the x's divided by n, that's your mean. So we can calculate it in kind of a brute force approach way, equals, and then click this cell, divided by, that's the /, and then click the other cell. So for me, it's A13 divided by A14. And that should give me a 7 once I click the enter key. Great, so that's our mean, or average. But that's kind of a lot of work here. We're using technology for a reason, to make our life easy. So if all I wanted is the mean, I would just type equals, and then you type in average. So average, and then click your cells here. And now we have the mean. Mean and average are synonymous. But there's other ways that you can calculate the mean. Different things that also try and represent the data and represent the center. So what are those other things? Well, one of them is the harmonic mean. One of them, let's go in order here. Let's start with the mode. The mode is the most frequent piece of data in a data set. So again, this is something that Google Sheets can calculate, and Excel. Type equals and then mode. Mode of 2. Okay. Not bad. There's the median. And for this, let me help you out. The median is what's in the middle of your data set. It's It's the point in your data set that separates the top half of the data set from the bottom half, if you were to list things in order. Now, to get things in order, click and highlight just your data. So highlight just that column of data. Let's go to data. Now you got to be careful because there's two things. The first one of them is sorting the entire column. I don't want to sort the entire column. I want to sort the data range that I selected. So sort the range. Now you can go from lowest to highest or highest to lowest, A to Z or Z to A, depending on what you want. I'll just go from A to Z like that. So nice. My data is now sorted in increasing order. Is everyone able to get that sort? So if I have 11 values, 6 is in the middle. There's 5 above and 5 below. So the median is 2. So that's our median. Now that we got that by looking at our data, what do you suppose that I have to do if I wanted it just to calculate it? If I said, you know, hey, Google, calculate this for me. What would I have to do? Just take a wild guess. Yeah, equals median. Thanks, Ryan. Equals median. And then select your data again. Now, you do not have to have all these commands memorized. If and when I need you to do something on Excel, say during a test, I'll give them to you. And on the back of your sheet, here they are. So here are your commands that you would use. There's two more that we're going to look at, the harmonic mean and the geometric mean. There's also root mean square. I'm not going to deal with that. You can. The harmonic mean is calculated by first finding the reciprocal of all your data. So if I take the reciprocal of 4 is 1/4, so I get 0.25. Reciprocal of 1/3, reciprocal of 2, I should say reciprocal of 3 is 1/3, etc. If you add these up, that's going to give you the sum of 1 over x. That's what that's giving you. Then if you take that sum of 1 over x and divide that into n, that gives you the harmonic mean. And the harmonic mean in this case was 1.964. That seems pretty reasonable. Let's go over to Google Sheets here. You can get the harmonic mean equals HAR mean, harm mean. And again, go to your data, select your data, and then you get the harmonic mean. Doesn't work out nice and even, but it's not too bad. Harmonic mean. Now there's also one that you should use when you're looking at the financial data. Earlier in this section, we looked at some financial data, and the simple average or arithmetic mean was a little bit misleading. So the last one that we're going to look at here is the geometric mean. And I'll show you just a little bit about that. Let's type in equals GEO. You can't get too far before you see which command to use. Geometric mean of our data. So geomean. Now, the big question for you is, are these values representative of your data set? How do you think 7 does? Is 7 representative of the data? Does that represent your data pretty well? No. How about the mode of 2? Does that represent your data pretty good? Yeah, I'd say so. And the median, same way. How about the harmonic mean? Is that a good representative of your data? That's not bad. Yeah, 1.96, sure. Yeah, I'd say that does pretty good. How about the geometric mean? Sorta, right? It's not bad. It's not perfect, but certainly it's better than the arithmetic mean, right? Arithmetic mean was just, yeah, it was worthless. There's one more that is just so bad that I don't ever use it. It's called the mid-range. The mid-range is the average of the highest and the lowest. So, but it's really bad. Let's take a look at the mid-range for this data set. What would the mid-range be here? 1 plus 56 divided by 2. Yeah, 57 divided by 2 is 28.5. How do you think the mid-range does? Is that representative of your data? No. Mid-range is horrible. The problem with the mid-range is that it's sensitive to outlying values on either end. If you had an extreme value that's high, extreme value low, or both, it's going to be sensitive to both. So I don't like the mid-range at all. And here's a little bit of a summary here on the reverse side. Some good and some bad things about this. The arithmetic mean. Well, the good thing is that it uses all of your data. I mean, sometimes it's a concern if you're ignoring or throwing out data. It's like, well, wait a minute. You collected that data. It's part of your data set. How come you're not using it? You should be using it. The bummer thing, as we saw, is that it can be sensitive to outliers. Now, these are measures of what are called central tendency. Measures of central tendency. It measures how your data clusters around a center, or what's typical. So these measures of central tendency have some good things and some bad things. The good thing about the mode is that it's not sensitive to these outlying values. The mode is simply what's most frequent. The bad thing is that you can be ignoring a lot of data. Okay. Harmonic mean is good when there's some extreme values. We saw that in the example we just worked. The downside of it is that people don't really know much about the harmonic mean. It's just not widely known outside of a math and specifically a statistics class. Same thing for a geometric mean. I'm going to go back and take a look at some things with a geometric mean. Root mean square is stuff that you would use in power calculations. That's not relevant to our class. So we're not going to discuss that. But you can use it in power calculations. And let's see, what else? Mid-range, harmonic, geometric, mode, arithmetic, median. One last statistic that I should put down here is the median. The advantage is that it's not sensitive to outliers. The disadvantage is that it doesn't use all the data. In fact, it ignores much of the data. You're just looking at what the middle number is. It still has its uses. If you pay attention to the news sometime, when they're reporting statistics on household income, they don't talk about the average household income. Why not? Well, if you're averaging Bill Gates' income with mine, it's like averaging billions of dollars with zero. Basically, you're going to get half of Bill Gates' income. All right, and that's not representative of anything. So you get a lot of extreme values in working with the average. That would skew the statistics for household income. So instead, they talk about median family income. So where's the 50th percentile? Where's that dividing line between the upper half and the lower half? That's what they'll talk about, because that's not going to be sensitive to those outliers. Yes, sir?
I'm curious, what is the mid-range useful for?
Nothing in my mind. I just don't use the mid-range. I mean, the author, I think, in one of the exercises asks us for the mid-range, and we can calculate it. You know, maybe sometime it's okay, but like I said, you're going to be sensitive to outliers on both ends. So in the example on the reverse side, I mean, our mid-range was 28.5. That seemed even worse than the average, which was 7. So yeah, the mid-range, I just don't think is very useful at all. And I don't recall seeing it used outside of this maybe one section. Yeah. So appreciate the question. Anything else on this one? Okay, so one nice thing that the author did here in this section when he reworked it was he gave you some questions to think about. And we're going to do that. I did promise to get back to you with regard to the geometric mean a little bit. The use of the geometric mean is best for, or one good place for it is financial data. So with respect to financial data, if you'd calculate the geometric mean for this data, it'd be much more relevant. You get a much better statistic. Here, the arithmetic mean was misleading. Now, the people who invited me to this seminar had their own statistic. They said, oh, we got the Sharpe Ratio, which also did a good job. We're not going to calculate the Sharpe Ratio here. 0.29 for this one, 0.91 for this one. Now, remember, there was a huge difference in their performance over time. 363,000 versus 1.174 million. So, yeah, it makes sense that this one is low and this one is high. But the geometric mean would have done the same thing. So a quick version of how to calculate geometric mean. You would take the product of all your data and then take the nth root of that. So if you have 3 pieces of data, and the example on the front side you can look at your leisure. This is the performance of your mutual fund or your stock over time. So it's up 50%. You write your 150% as a decimal, and then it was down 50%, 50% as a decimal, 0.5, etc. And then up or down another, no, up at 20%. So multiply these together and take the cube root of that, and that's your geometric mean here. But geometric mean is good for financial data, and it'll be much more useful in evaluating the performance of these funds. In fact, if you look at the geometric mean, it would tell you exactly what you need to know from this data set. One of the things that I'm anxious for you to know and be comfortable with after this discussion is some of the advantages and disadvantages of these various means. So before we move on and discuss some of the homework problems, is there anything you'd like to follow up on with regards to this discussion here? Looking good on that? Yes. How it's calculated? Or sure. So the harmonic mean, what you have to do to calculate that, if you were doing it by hand instead of letting Google Sheets do it for you, is you have to take the reciprocal of your data and then add up all the reciprocals. So like the reciprocal of 4 is 1/4, 3, 1/3, etc. If you add up all those reciprocals, that's this total right here. So that's the sum of your reciprocals, and then you divide that sum into how many pieces of data you have. So in the case of the front side, that was 11. And that gives you a different look at the average, a different statistic for it. And this one turned out to be a little bit less than 2, which seems better in terms of saying, okay, well, what's typical of this data set? Yeah, about a 2. 1.96 is where it ended up. So it's just not something that most people are familiar with. That's kind of the downside. If you say harmonic mean, they're going to look at you sideways. All right. Other questions from this columns or this side of the sheet right here. All right. Hopefully you're comfortable with that. Let's answer a few questions from the book. And like I said, I like these because they're think questions. They ask you to go a little bit more, a little bit deeper than simply answering, okay, the mean is this, the mode is this. They ask you to think a little bit. We'll start out with problem number 10. This is biologists conducted experiments to determine whether a deficiency of carbon dioxide in the soil affects phenotypes of peas. Listed below are phenocodes where 1 is smooth yellow, 2 is smooth green, 3 is wrinkled yellow, 4 is wrinkled green. Can the measures of center be obtained for these values? Do the results make sense? So the author considers the measures of center to be the mean, median, mode, and mid-range. I've already discussed the mid-range. We're not going to do the mid-range. It's just not of interest to us. So the mean, median, and mode. Can we calculate those? Yes. In fact, let me spare you the effort and give you the actual values for those things here. So in problem number 10, the mean, and I'm going to denote that with X bar because this is a sample mean. The mean is 1.9. The median, I'm going to use some notation here that those of you que han tomado una clase de español might recognize as a tilde. The median is 2. The last one here is the mode. I don't have any notation for that. The mode is 1. So you can calculate those statistics for your data. Do they make sense, though? Does it make sense to find the mean, median, and the mode for this data? Don't make me pull out the Jeopardy music, all right? Come on. What, yes?
It wouldn't make sense.
Good, why not?
It wouldn't make sense because the characteristics, you're not really finding a number.
Yeah. Yeah, it doesn't make sense to average smooth yellow with smooth green with wrinkled yellow and wrinkled green. I mean, there just happen to be names. And then you gave them a number, averaging those, well, it doesn't really mean anything. So, yeah, it doesn't help us out because the data is the wrong type. The data is really just nominal data. There is one statistic here that does make sense, though. Which one is it? The mode. Yeah. What's the most frequent? Okay. The most frequent was smooth yellow. All right. That makes sense. So it does work out okay to talk about the mode in this particular case, not the other measures of central tendency. Let's move down to cell phones. There's been a lot of work on this, and so far I'm not sure that it's been really conclusive. Some studies find a relationship, some studies don't. But there is legitimate concern about the amount of radiation you're absorbing from your cell phone. So listed below here are the rates of radiation absorption for a bunch of different phones. The FCC recommends that a phone has an absorption rate of less than 1.6 watts per kilogram. Again, you could calculate the average, but is the average the statistic that you would want from this data set? If you're worried about the radiation that you get from your cell phone, are you going to be calculating the average of this? What are you going to be looking for? Yeah, the lowest. There's only one statistic you care about, and that's, all right, which one's the lowest? Let's see, which one is the lowest? 0.74, 1, 2, 3, 4. Oh, yeah, here we go, 0.51. So, second to last one, let's see, which one would that be? LGG2. All right, cool. So, there you go. You get one that's pretty benign. Yeah, so there's other features in the data that you would want to look at beyond just, well, what's typical? Where's the center? We're going to see that again in the next one. We're going to be asked to do a little bit of thinking. Are we good with problem number 12 here? Okay. Let's move on to problem number 14. Listed below are the number of heroic firefighters who lost their lives in the United States each year while fighting forest fires. The numbers are listed in order by year, starting with the year 2000. What important feature of the data is not revealed by any measure of the center? So yeah, you can calculate the mean, the median, the mode, but there might be something in this data that's lost if you just squished it down to one number like that. I'll kind of give it a little bit of a hint. This is the year 2000, 2001, 2002, etc. All the way up. What might be missing from this if we just looked at a number? Yeah.
Might be like emotional impact, because some might be.
Okay. Yeah. Could be, some of the emotional impacts. But statistically speaking, what might be missing is any trends, right? Is the trend going down? Are we getting better about fighting fires without fatalities? Certainly not at this last year. There's quite a spike there. Let's take a look. I think I might have that one plotted still. Let's see, is it here maybe? No, that's not it. Too much data. No. All right. Let's do a quick plot of the data. So go back to a sheet that you have open in Google Sheets. Let's open up a new spreadsheet. The data started in the year 2000. So I'm going to type in 2000 here. And I'm going to need some subsequent years. So in the second cell of my data, I'm going to take this and add 1. And then just copy this cell all the way down to, fairways. I'm going to go down to 14. I'm not sure exactly how much data there is there, but I think that's about right. So it's a nice trick. That way you can get everything numbered quickly. So what you do is, after the first cell, you click the second cell, you type equals, click the first cell, +1, or +10, or 15, or 5, or whatever you're incrementing by. And then you hit enter. And then you can copy that formula. So Control C or Command C, depending on what you've got, and then paste it the rest of the way. What's that?
Let's say with the box, you can just drag it too.
Oh, will it just drag? Cool. So the idea is not to have to type in all these things. Now let's throw in the numbers here. So 20, 18, 23, 30, 20, 12, 24, this should be in 2006, 9 in 2007, 25, 15, 8, 11, 15, and finally 34. Wow, whopper there at the end. Once you get your data set in, all entered, then let's highlight that data and insert a chart. And I'm hoping that it gives me the chart that I want this time, not the chart that it wants. So click Insert, down to Chart. Cool. So what's missing is that you can't see what's happening over time. Now, over time, other than this last year where there's a big spike, over time it looks like, there's a little bit of a downward trend. There's also another kind of a curious thing here. You got these spikes every couple years. Spike here, spike here, spike here. So I can't make anything of it. Certainly everyone would like to see this trend go down. But the big point of this is that what you're missing here is, or by calculating, say, a mean, is if there's any trend in the data. That's the concern for problem number 14. Let's take a step back and look at problem number 6. We had some argument discussion on this in my morning class, so let's see what you guys think. There we go. Listed below are the weights and pounds of 11 players randomly selected from the roster of the Seattle Seahawks when they won Super Bowl 48. Are the results likely to be representative of all National Football League players? So, do you need practice calculating the mean and standard deviation, or the mean and median mode on Excel? Okay, we're good on that. Google Sheets, Chabelle, good on that? All right. So the question is, you've got all these weights of 11 randomly selected players. Do you think these are likely to be representative of all National Football League players? If you selected 11 players at random from the NFL, are you going to get something similar, do you think? Got to vote for yes? Well, if you went to any team, and I guess this is what the authors are arguing, any team, you're going to have some linemen, and I'm supposing that this may be the kicker, etc. So you're going to have the same amount of running backs, tight ends, linemen, kickers, quarterbacks, etc. And they're all going to have similar weight profiles. You're not going to have somebody who's 300 pounds punting your ball. All right? You're not going to have the 189-pounder on the offensive line either. So they're going to be similar. So overall, this should be representative. And there's one other aspect to this that I think lends credence to his argument, and is the players were randomly selected. It's not a voluntary response kind of thing, which we've talked about a couple times. In fact, in every class till now, voluntary response leads you to data that's just not something you can generalize and work with. So it's only representative of the people that were in the survey, and that's it. So yeah, in this one, it's probably representative, but we can start quantifying that later in this course. Where do you think that the true average weight of football players in the NFL is. We can start making more sophisticated statements about that starting in Chapter 7. All right, there's one last thing we want to do and discuss in terms of Google Sheets, and that is finding the mean of frequency data. Let's go back to a data set we used the other day. We talked about classes of data, class width, midpoint, etc. And that'd be problem number 30. In terms of problem number 30, let's do a couple simple things first. First things first, nice little reminder here for you. What's the class width? 10. Good. Remember, class width is going to be the difference between adjacent lower class limits or adjacent upper class limits. So 59 minus 49, 40 minus 30, etc. The class width here is 10. Let's start with the class midpoint for the first class here. What's that class midpoint? Thanks, Logan. 24.5. And then the next one, 34.5. And it's just going to keep on increasing by 10, 44.5, 54.5, all the way up to 74.5. So those are the class midpoints. You have your lower class limits and upper class limits, 20, 29, etc. So a little bit of review there. But what if your goal was to try and find the average of this data set? Now there's one big problem. We don't have the original data, do we? We have to come up with some way to represent that data, even though we don't have it. And the way to do that is to use the class midpoint to represent your data. Now, let me write down the formula that we're going to use to find the mean of a data set from frequency data. So, mean from frequency data. So again, call that X bar your sample mean. Overall, whenever you calculate the mean or the arithmetic average, it's going to be the sum of the data divided by the count. And that's going to be the same thing here. The count, however, is going to be the sum of the frequencies. So F is frequency. And X is going to be the data. Now, in this case, in order to calculate the sum of the data, you're going to have to take, however many people are in the first class, 24.5, and multiply that by the frequency, so X times F. So if you have 10 people in that class, well, then it's 10 times 24.5. Let's set this up in Google Sheets. So I can get rid of this. Oh, one quick thing. If you have a chart here, sometimes it's convenient to move that chart to its own sheet. That way it kind of puts it someplace handy. So now it's here on its own sheet. I can click back here to sheet 1. There's my data. And here's chart 1. So if I want to get one or the other, I can just click on its own sheet. So that is kind of a convenient feature here. I'm going to open up yet another new file. Let's calculate mean of this data. So we'll start out with 24.5. And it's up to you. You can just type in 34.5, 44.5, etc. I'm not going to do that. Some people call it laziness. I prefer to think of it as economy of movement. So I'll click this, and I'll add, this time I'm going to add 10. And let's copy that all the way down here. I might have an extra one. Yeah. I don't need this last one of 74 or 84.5. So that's good enough. These are my X's. That's where my data is. I'm considering everybody in, say, this age group to have had a birthday that put them at 34 and a half years old when they won their Academy Award. We need to type in the frequencies here. Let me give those to you. 1, 28, 36, 15, 6, and 1. Now, we're going to have to find a couple things here. One of them is we have to figure out how many people are in our study. That would be the sum of your frequencies. So how many people are here? Well, let's just sum up this column. So there's a total of 87 people in this data set. Okay. Just going to do a check of the sound here. Recording devices. Yeah, we still got some sound. Okay. So that's how many people are in our data set, but we need to figure out the sum of your data. Now, a brute force approach would be adding them all up. We have one person who is 24 and a half years old, and we'd have to add up 28 people who are 34 and a half years old. Rather than add it up 28 times, the faster way is to multiply. So that's going to be this new column. Hit the equals key, then this column times, that's going to be the asterisk. You'll find that on your keypad or above the 8 times this column. Once you get those two in, copy it and paste it down to the remaining 5 of your columns. Now that's good. We're getting closer. But I need to total that up. So again, that's a sum here. Almost done. I've got my numerator and I've got my denominator. If I wanted the mean, then what do I need to do? Equals what? I don't want to do the average because I don't have the original data, so I can't really just calculate the average. Well, I've already got my sums. What I need to do is this last little piece here, because I've got that sum and I've got this sum. I've got both of those. The bottom one was 87. The top one was in the 3000s. So all I need to do is divide those two. So going back here, you can type equals this one. So that's the sum of your x times f divided by this one. And this worked out amazingly even. Is everyone else getting 44.5? Somehow or another I expected something that was going to be different than that. But it worked out nice and even. 44.5. So a big question for you is this. If I had the original data set, would that value equal the mean of the original data set? What do you think? Maybe. Okay. Would it equal the mean of the original data set? Okay. We got somebody who says yes. Heather? Sure. So going back here, so what I need to get the mean here is the sum of these two pieces of data, or I mean the quotient of those two, because this is my numerator, it's the sum of the frequencies. This is my count, that's how many pieces of data I have. So it's just the quotient of those two. So it would be equals, and then you click on this cell, divided by this cell. And then when you've done that, you should be able to type enter. All right, thanks. So back to the question. If I had the original data set, if I had, instead of frequency data, if I had the original data set, I calculated the mean, would I get 44.5? Kayla, what do you think? Gonna vote for yes? Amila? You agree? Don't know? No? Don't know why? Dale? Austin?
I think it might be close, but the original data set might be different.
It should be somewhat close. It depends on how good 34.5 represents all the people that are in this class. I mean, if this is a close representative, yeah, then this should be pretty close to the means you get from the original data. But it's all going to depend on how good these numbers here are representing all the values in this class. I mean, you got 36 values in this class. It's not likely that if you average those, you would get 44.5. Just probably wouldn't happen. So the farther away that the average of your original data set is from these class midpoints, then this is going to struggle to be representative. But it should be reasonably close. It can't be too far off. Now, I've been using statistics, or using some notation here to represent these things. Let me remind you of a couple things here to wrap up this section. So let's go back to here. I've been using X bar to represent this. Now, X bar is the sample mean. Sample mean. X bar. I could also work with the population mean. What's the difference between the sample and the population? Yeah. Population is the whole thing. A sample is some subset of it. When you're dealing with the population mean, you're going to use a parameter. It's called mu. When you're dealing with the sample, numerical values you calculate from a sample are called what? Statistic. Well done. I thought I was going to have to send you guys chasing into your notes or something like that. Well done. So a sample leads to a statistic, whereas if you have data from the entire population, that's a parameter. And we're going to denote those different. Now, for the mean, the calculation is the same. You add them up and you divide by n for both of those. But later on, we start dealing with measures of dispersion. Then the calculation actually starts to get a little bit different. But for right now, they're calculated the same. They're just different notations. All right. Good job. Are we okay with measures of central tendency? Like I said, on an exam, I would give you the commands for anything that you would need to calculate, but you need to interpret it. You need to know the advantages and disadvantages of each of these so that you know where to use them. Geometric mean is good for working with data regarding interest, compound interest. Arithmatic mean is sensitive to outliers, but at least it uses everything. And the mid-range is just trash. We're not going to use it at all. So, for homework, try from the 12th edition, try 1 through 31. From the 13th edition, 1 through 21, 29, and 31. Good luck.